Hi, AP Calculus students. How you doing today? Today we're doing section 3.3. There'll be 3 videos, I think, in total for this section. The first one, just the basic notes, and then we'll have examples for later parts of this section. I think I divided 3.3 into A, B, and C. So let's first start with our notes. This is called the first derivative test. And as I put, it's so incredibly important. You will use this a lot on the AP exam. And the way that we apply it is we usually set it up in a chart as we have over here. So again, what's happening in section 3 is you're not learning any new derivative rules. You're just applying them. Okay, so you learned how in the prior sections of chapter 3, how to find maximums and minimums, how to find extrema on closed intervals. So what we're doing today is, can we find maximums and minimums on functions that are not on closed intervals? For instance, just a cubic function on its domain from negative infinity to infinity, can you find the max and mins? And can you find where the function is increasing and decreasing in between and before and after those maximum and minimum points? So we're using calculus to find all the important characteristics of a function on its domain. Okay, so the first derivative test. So number 1, functions have increasing, we abbreviate with INC, save ourselves some time, and decreasing, DEC, intervals between before and after max and mins, right? That's where critical points are. So as you can imagine, we are going to be still using critical points. And it does say C below, right? So when you look down here, I just made a kind of a cubic graph, and I made a maximum point here. Notice that before, to the left of this maximum point, the function is increasing. And in fact, if I drew little tangent lines, they would all have a positive slope, meaning the derivative would be positive, right? The derivative would be 0, or a critical point at the maximum. Notice to the right of the maximum point that that is a decreasing slope here. If I drew little tangent lines, those slopes would be negative. The derivative would be negative, right? Here's a minimum point, right? If I drew a little tangent line at the minimum, critical point, the derivative would be 0. Before that time, to get to that minimum point, the function was decreasing, right? The derivative is negative, right? After that, to the right of that minimum, the derivative would be positive, right? That's what's making it increase out of that minimum. So number 2, we will use the first derivative test or chart. To the right, I forgot a T right here. Look, I used that T twice there. To the right, to find all relative maximums and minimums, right? And all increasing and decreasing x intervals. Again, increasing is where the derivative is greater than 0. Decreasing is where the derivative is less than 0. Notice max and mins are occurring where the derivative is 0 or undefined, right? So number 3, a maximum occurs at a critical point where the derivative is greater than 0, positive, to the left, and less than 0, negative, to the right. A minimum occurs at a critical point where the derivative is less than 0, meaning negative to the left, and greater than 0, meaning positive to the right. There is no maximum or minimum if the derivative does not change at a critical point, right? That would happen on the cubic x cubed function where x equals 0. There is a critical point there, but that function is always increasing. No matter where you draw a tangent line, the slope will be positive, and so the derivative doesn't change sign. Number 4, the first derivative test will be a justification you use often on the AP exam, but the readers will not decipher your chart for you. So when you fill in a chart here and the AP readers are looking for maximums and minimums and where the function is increasing or decreasing, they will not interpret your chart. You have to interpret your chart. So you get your information from the chart and then you write out increasing intervals are here, decreasing intervals are here, maximums, minimum points, right? So we're going to do example 25 and 15, and we're going to do that on this chart over here. So here is your incredibly important first derivative chart. I'm going to see if I can just give us a little bit of room there. There we go. Okay. So here is the chart that we'll always use. Is the top row will be your interval. Okay. Your interval are x intervals over the entire domain of the function you've been given, and it's broken up here by critical points and discontinuities, right? If there's a discontinuity in a function where a point doesn't exist, often a function will increase or decrease or change over that discontinuity. And so we break our x intervals up by discontinuities and critical points. The next thing we'll do is once we have those intervals written, we will write a test value. So easy. We just pick a value here, here, and here that's in the interval that we wrote, right? There's an infinite number of test values in any interval. So we just try to choose the easiest, okay? Then we're going to write the derivative, right? And we've already have, right? Because if we had to find the critical points, we've already found where the derivative is 0 or undefined. So now we're going to use it. We're going to put our test value into that derivative, right? Which makes sense because we need to fill in the next row. So we're going to put that test value into the derivative to see whether it's positive or negative. And then we can easily decide if the function is increasing or decreasing. There we go. And then from there, with the critical points and seeing increasing and decreasing intervals, we can see where the maximum and minimum points are. Let's remember these are points. So for our x's, where we find relative maximums and minimums, we are going to have to find the y value that goes with that point. Okay, so let's first try on number 25. On number 25, they give a function x to the 5th minus 5x over 5. There we go. Let's make sure that I wrote that right on number 25. I did. Okay, so I think that it's actually best to write this function though. You can keep it like it is, but I'm going to separate it into 1/5 x to the 5th minus, right? And then we have x here. There we go. Okay, so the first thing I'm going to do then is check. First of all, for writing my intervals, are there any discontinuities anywhere where this function itself is undefined? No, it's a polynomial. It's defined everywhere. So now I need my critical points to break up my intervals. So I'm going to take the derivative and find where the derivative is 0 or undefined. Let's go ahead and do that. So the derivative would be when I bring the 5 out front and multiply it, it cancels out that 5. I have x to the 4th minus 1. Okay, for our critical points, undefined, where is this derivative undefined or 0? It is defined everywhere because it's a polynomial. Where is it equal to 0? Well, when I add a 1 and take the 4th root, I get that that happens at x equals plus or minus 1. Right, so again, I set x to the 4th minus 1 equal to 0, add a 1, take the 4th root, plus or minus 1. So what are my intervals? Because this is a polynomial, I have to cover the entire domain of the polynomial. And polynomials are defined from negative infinity to infinity. So let's go ahead. We'll start at our lowest x in the domain, negative infinity, and we get stopped at an x of negative 1. Okay, my interval then must start at negative 1 and get stopped at a critical point of 1. Okay, from there, my last interval, I start at 1. I have no other critical points, and so it goes to infinity. Test values, let's pick some easy ones. a great value in between negative infinity and -1, -2. Between -1 and 1 is 0. Between 1 and infinity is 2. Right, again, I could pick 100 right here for my test value and we would be just fine. Okay, now let's check. We use these test values and we're going to check them in the derivative, right? We need to fill in this next row and see what the derivative is doing. When I put a -2 into the derivative, -2⁴ is 16 minus 1. This is obviously positive. I don't care what the actual output is, just if it's positive or negative. When I put a 0 in to the derivative, I get a negative out. And when I put a 2 in, once again, I get a positive out. Okay, so it's really easy to say then where the function is increasing or decreasing, right? Positive is increasing, negative is decreasing, and positive is increasing again. Okay, I kind of took up my room here. So there we go. Where are the maximum and minimum points? Well, let's take a look here. Maximums or minimums occur at critical points, right? So that's what these arrows are for here. There's a critical point at -1. There's a critical point at 1. Let's take a look. So right here, I'm going to have to erase a little bit. It's okay. I wrote really big so that you could see. Here we go. There we go. So right at this point here where x is -1, notice the derivative is increasing and then decreasing. That makes a maximum. So there's a relative maximum here at -1. I have to find the y that goes with that. And let's see here, critical point at 1, the function is decreasing then increasing. That makes a minimum at 1. And I need the y value there. So this means that I'm going to have to write the function again to find the y value that goes with it. So let's go ahead and do that. I had written that function as x to the 5th over 5 minus 5x. So when we put a -1 in here, we get a -1/5 plus 5, right? That was, sorry, I wrote it this way. I'm okay now. There we go. Okay, I wrote it this way, right? Yeah, I did. Okay, I'll be right with you. I'm gonna check. I did. See what happens when you don't have enough board room? Okay, there we go. Now when I put a -1 in, this is a -1/5 plus 1, which is 4/5. When I put a 1 in, I get 1/5 minus 1, which is a -4/5. Okay, so what's my conclusion? My conclusion is that this function is increasing from -infinity to -1, and then again from 1 to infinity. This function is decreasing from -1 to 1. There we go. And that these are the maximums and minimums, right? So I did put this on the calculator just so you could see right here what the function looks like. Look at that. We were absolutely right that this function has a maximum at -1 and a minimum at 1, and that it is first increasing, then decreasing and increasing. Pretty cool, huh? All right, now the next thing we're going to do is number 15. Now, of course, I did this number 15 because it's trig, okay? This one in particular is a little tougher, but I figure we can do it together. So the reason why I'm telling you this is because when you see trig and you're using the first derivative test, in general, it'll be easier than the one we're going to do together. So please don't be frightened of it. Do it step by step. Okay, so just restarting this. So we're going to find a few places where we're going to have to really think about what we know about trig expressions and do some logical thinking too. Okay, there we go. Let's restart our chart. Number 15. Now, on number 15 in your book, just making sure I wrote it right. Hold on. There we go. Okay, on number 15 in your book, they are asking for just where the increasing and decreasing intervals are, not where the maximums and minimums are. But I still just really felt that we should do it because they could ask you for that. And so we're going to go ahead and do everything. Okay. So first of all, our intervals are broken up by discontinuities and by critical points. So discontinuities, this is a linear function here, x. This is the trig function cosine. There are no discontinuities in either function, and same with the subtraction of them. The domain is going from 0 to 2 pi, not from negative infinity to infinity. Okay, so first we need, next we need some critical points. So let's take the derivative. That would be 1 plus 2 sine of x. Let's see, 1 obviously here, and then we have the 2, and the derivative of cosine is a negative sign, and now it's positive. Okay, let's do those critical points. Undefined and equal to 0. This expression is defined everywhere. DEW, defined everywhere. Where is this equal to 0? This is going to take us a little bit. So when I set this function equal to 0, right here, I will subtract a 1 and divide by 2. And I get that sine. I'm looking for where sine of x equals a negative 1/2. Okay, this is going to take us a little bit, right? So first of all, where is sine 1/2, right, in the first quadrant? So let's see, that would be at pi over 6, right? But notice that our value is negative. So sine is negative in the third and the fourth quadrant, and the angle must be pi over 6 there. So we just have to name these angles. This is the angle 7 pi over 6. And this is the angle 11 pi over 6. Okay, there's our critical points there. Okay, so let's go ahead and fill in our intervals across the entire domain that they gave us from 0 to 2 pi. Okay. First of all, our lowest x value is a 0, and we get stopped at 7 pi over 6. We start with 7 pi over 6 and stop at 11 pi over 6. And next we start at 11 pi over 6, right, and go to 2 pi. And we have covered the entire interval. Okay, test values. Let's pick an easy value between 0 and 7 pi over 6, right? How about pi over 2? Let's pick an easy value between 7 pi over 6 and 11 pi over 6. How about 3 pi over 2? Okay, now as I talked about, here's one of the difficult steps that comes in. Take a look here. We want to pick a test value in between 11 pi over 6 and 2 pi. Well, on our unit circle, we don't recognize really any angle in between there, right? And so, well, we have no angle on the unit circle in between there. So what we're going to do is, let's go for halfway. Right, so here's 11 pi over 6. So halfway here then would be, right, this is 30 degrees and half of that would be 15 degrees. Okay, so let's think about this. If pi over 6 is 30 degrees, then 15 degrees, halfway in between there must be pi over 12. Yes? Okay, now pi over 12. All right, so I must be, and notice I am 1 pi over 12 away from 2 pi, right? So meaning that this angle right here then would be over 12. Let's see, I said I'm 1 short of 2 pi. There we go. Let's take a look. That's a little weird, right? 24 pi over 12 would be 2 pi, right? And so if I was just 1 short, that would be 23 pi over 12. Okay, so that was a little sticky point you don't usually come across when you're doing these problems, but hey, together we can do this, right? Okay, now let's actually test that derivative. Now be careful, don't use your test value in the original function. We're testing the derivative. So I usually circle it and go, okay, that's where I'm looking right there. Okay, so let's go ahead. When we put in pi over 2, sine of pi over 2 is 1, right? And I can see this is going to be positive. At sine of 3 pi over 2 is a -1. I can see that this is going to be negative. Okay, now we come to this difficult part here also. All right, my son's coming. Is my son coming in? Yes. Hi, Alex.
What are you doing to them? It's Saturday.
Oh, they don't know. I'm recording this for later.
Oh.
It's my son, Alex.
What do you mean they don't know?
Yeah, it's a good thing we got a little break talking to you because this part is really tough right here.
Oh, good. You're welcome.
I'll be done in just a couple minutes. Okay. So anyway, so now you're like, well, okay, now you're going to, Ms. Culver, you're going to make me put 23 pi over 12 into this derivative. I don't know if it's positive or negative, right? Because you're not supposed to have a calculator in your hand. We're going to have to go back and use a little logic here. Okay, here we go. Let's go back to 11 pi over 6. Now, what we absolutely knew was that at 11 pi over 6, the sign was a -1/2, right? We figured that out, right? That's what we said. Okay, now, and that made the derivative 0. Okay, so let's take a look here. At 23 pi over 12, at this dashed line right here, notice that that sign right here is smaller, right, than the sign, right, because it's the y value, is smaller than the sign here, which we said was a -1/2. So this sign is smaller, right? Maybe like a -1/4, something -1/3, close to that, right? So when sign is a -1/2 right here, I know I get a 0. So if sign is less than that, like a -1/4, notice that this expression will remain positive. 2 times a number less than -1/2 is not going to overcome this +1. So it must be positive, right? Again, you won't run into this often in your book, but hey, at least we get to talk about it. Okay, easier part, increasing, decreasing, right, and increasing. Okay, relative max or mins. All right, let's take a look here. So just getting rid of a little bit of work here. I'm going to move this function down. Okay, let's see. Critical point at 7 pi over 6, increasing, decreasing, right? Increasing, decreasing, that's a max at 7 pi over 6, right? Critical point at 11 pi over 6, decreasing before, increasing after, that's a minimum. At 11 pi over 6. Okay, and then what we would do is into the original function, we would put 7 pi over 6 here and here, right? And 11 pi over 6 here and here. We might as well keep going. It's kind of ugly, but we're going to do it. Notice when you put in a 7 pi over 6 here, you have 7 pi over 6 minus. Now, cosine is 7 pi over 6. Let's draw ourselves a picture here. 7 pi over 6 was right here, right? So cosine of pi over 6 is the square root of 3 over 2, and it's negative in the third quadrant. So 2 times a negative square root of 3 over 2. And that makes a positive, and we get 7 pi over 6 plus the square root of 3. Okay, a little tough, right? Okay, 11 pi over 6. When we put it into the function, we get 11 pi over 6 minus 2. Now, again, cosine of 11 pi over 6 right here, still the square root of 3 over 2. Notice it's positive in the fourth quadrant. There we go. And we end up with 11 pi over 6 minus the square root of 3. So our conclusions are, here's our maximum and minimum points. And we can also include that the function is increasing from 0 to 7 pi over 6 and from 11 pi over 6 to 2 pi. The function is decreasing from 7 pi over 6 to 11 pi over 6. There we go. And there's our conclusions. Now, just in case we haven't covered it, why the parentheses? Why not brackets, right? Because the function is increasing from 0 to 7 pi over 6. We know at 7 pi over 6, it's 0. The derivative is 0. It's neither increasing or decreasing, right? So same with the decreasing. We know the function is decreasing between 7 pi over 6 and 11 pi over 6. But we know at these values that the derivative was 0. So we don't have brackets. We don't include those because a zero slope is neither increasing or decreasing. So thanks for hanging out with me. I know it took a while, but I hope that you found it understandable, and we'll be doing more example videos later. Have a great day.